Hello, hey everyone. We are going to be talking about radar meteorology today. And as you know, we've got this large PowerPoint. And we've already kind of looked at some things, but I'm going to go through the first half of it up through Doppler radar on this lecture so that I don't have to take the time during class to go through it in detail. We've already gone through a lot of it, so this should be relatively quick. So let's go ahead and share the screen. And we're going to start right here. Now, the first thing that we really need to talk about, and this is where it's going to be really important that you're paying attention and taking good notes, is when we talk about something that's a sensor, something that measures information. That's what a sensor does. And there's going to be two types of sensors. So the first separation, the first delineation is remote versus in situ. The second one is active versus passive. So, but you wouldn't call it just one type. You would combine them. So you would have remote active, remote passive, in situ active, or active in situ passive. Those are the four that you would have. So let's talk a little bit about this. The key thing between remote and in situ is that in situ is right here. For instance, a thermometer is in situ, meaning where am I measuring the temperature? I'm measuring the temperature right here where I'm at. A remote sensor says I'm more interested in finding out information over there. So a satellite is up in space looking over there at the Earth. A radar, like we see here in the picture, is looking at a thunderstorm over there. That makes it a remote sensor. So the most important remote sensors are radar and satellite. Now, we also talk about eyes. Are eyes remote or are they in situ? What do you think? Well, the reality is eyes are remote because I'm looking over there. The only feeling or the senses that are in situ would be like taste. Taste is right here. Feel is right here. Hearing is a little bit different because the object is making the sound over there, but we are receiving that information. The disturbance is here. So ears are really going to be in situ. You don't have remote hearing. Now, if you watched Harry Potter, they have the extendable ear things. That would be remote sensing hearing, but we're talking in situ. But your eyes are remote. They're looking over there to see information that's over there. Now, active versus passive. Passive means that you don't have to do anything to get information. So your eyes are a passive remote sensor. All I do is look over there and I'm getting information. The information comes to me. My brain processes the information. Unless you're a superhero and you had active remote eyesight, which would mean like you're throwing out lasers from your eyes. That might do it. The same is true with hearing. Hearing is just receiving. Now, there are animals that have an active hearing sensor, like bats, when they have echolocation. I was very young, and I had a kid next door that was like 7, 8 years older than I was, and he was totally blind. And he would walk around the house going and making that clicking sound with his mouth. And he would walk slowly and he would identify where all the objects were because he developed such a great sense of hearing that he could actually use echolocation to go, okay, a tree is this close. He could hear the difference between and how far something was away. Amazing ability that he developed without having visual senses. So that would be using this as an active sensor. But for the most of us, we just go, oh, I hear that, and then that's what we've got. Now, active means we've got to send out a signal. So think about radar, right? Radar is a perfect example of a remote active sensor because it sends out information, it sends out the pulse, and then here's the return signal. So it is definitely an active sensor looking at thunderstorms that are over there. Satellite is just out in space. It takes pictures or it receives information, but it does not send out information. Now there's, just to be technical. There are some satellites that are also like radar that send out signal. But for the most part, the things we see on TV and the weather site are just satellite images of being from a remote but passive sensor, just receiving information. The fact that it sends that signal to us to receive it doesn't make it an active sensor. Okay, now, did you write those examples down? Because you really should have. If you didn't do that, then you're not taking good notes. If we're going to look at a thunderstorm, we're going to have to use remote sensors. It's very difficult. You can't, the only in situ sensor that could help in a thunderstorm is if we launched a balloon into it. And launching a balloon into a thunderstorm, and they've tried to do this, is not very successful because lightning will often hit the balloon and destroy it. So they get some data until it gets destroyed, and then it's not really useful. So we're going to use remote sensors, and we're going to use a lot of stuff in this class using our eyes. So visual clues. We've already talked about rock hard texture, or glaciated, or looking for the overshooting top, or the strength of the back sheared anvil. Lots of things we can look at are visual clues. But the best way is to really get inside the storm, and that's to use radar. So we say it here on this last bullet point, radar lets us interrogate information. It detects precipitation, and then Doppler radar allows us to see which way that air is moving within the storm. So we've already said that radar is an acronym, should be on your list, radio detection and ranging. NEXRAD is a acronym as well, Next Generation Radar. WSR-88D, another acronym. Did I say a acronym? An acronym. Weather Surveillance Radar, 1988 Doppler. Here's the location. We've already kind of talked about this in class. We have a really great network. The United States is premier in Doppler radar and getting good information and good networks that allow us to survey or surveil the atmosphere. And we've already talked about this. We have the top-down view, which is a PPI, and then we change the azimuth angles. But if we stop, we could change the elevation angles, and that gives us an RHI. Put those two things together, and we get a volume scan, and that's where the term VCP came from. Here we've already talked about radar coverage. All the blue area is going to be fairly low to the ground. Remember, the further we are from a radar, the higher up in the atmosphere we are. Now, here's the new thing that we really haven't talked about. We have talked about improvements of the WSR-88 over the 88D over the 1957 radar. And the most important thing is sensitivity, which we've already talked about. How well can I hear faint echoes? We have a bigger radar dish. We send out more power. We have better listening techniques. We have a narrower beam. All those things make it more sensitive. Longer pulse makes it more sensitive. I hope you have that marked down. Now we're going to talk about the another improvement, which is reflectivity information displayed in the gate size. So this is going to be about resolution. Now this resolution, if you look, notice that the areas where I shade in the different colors, the yellow, the blue, the green, are much narrower here, and they're wider here. And then when I go out really far, all those like little rectangle-y type things is going to be larger. The smaller those are, like a pixel on a camera, the better the resolution. So these little areas that we assign colors are called gates. Now, the colors represent, in this case, a reflectivity. There's a computer that assigns color to a gate. There's a computer program, algorithm, that assigns color to the gate. That is called the VIP, the VIP. VIP stands for Video Integrator and Processor, both words with ORs. Video Integrator and Processor. And basically the color is assigned to a gate to indicate the reflectivity that is occurring at this place. They are not shaded. It's like one part of the gate is not bright orange and the next one's dark orange. A single color gets a gate. This the same thing is true in graphical image formats, GIFs, or you might say GIFs or JPEGs. They have pixels that are really small, and each pixel gets a color. We actually have 256 shades of red, green, and blue, and that gives us a color for that pixel. Put enough pixels in there, we pull back, and it looks like a picture. But really, we're just shading in very small squares. The smaller the pixel, the more that you can fit in your image, the better the resolution. So the only difference here is, and I need to bring out my good old Epic pen, is that the gate is not truly a square. And I'm going to exaggerate what it is by saying that it is really this way. Well, let me redo that. It's this way and this way. It's sort of pie-shaped. And you have to think that it's pie-shaped because the radar beam is spreading out. That is probably the worst picture. How about if I just go straight line to the radar? There's the beam going out. And when the beam goes out, I'm making areas where I can make little segments called gates. And that's the shape of it. So the shape of it is actually more like this, if I exaggerate. Now, the idea of this gate size is that this area is the pulse length. And this distance is the angular beam width. And that's what's determining the size of the gate. Now, continuing on, there's the pulse going out so that we get a pulse volume. It's three-dimensional chunk of pretzel dough flying through the atmosphere. The pulse length is the same no matter where it is. So this, when we go back here, the distance from the radar to the end, back and forth of the gate is the same no matter where I am. They're getting wider. And the reason they get wider is because it's a conical section. This pulse volume is a segment of a cone, and the further out you go, the wider it gets. Okay, so that's your beam width. Now, right now, our radar that we say is about 1 degree. And 1 degree, well, actually, if you look, it's more technically 0.95 degrees. But 1 degree, make it easy. The radar tends to look out this way. So the beam center is, if we imagine it being horizontal, would say that about half the beam, let's say about 0.5, and this way is about 0.5. Now, if I sent the beam out horizontally, do you see that half the beam would be hitting the ground? And that would cause a scattering of radiation back, and that would be very bright because the ground can reflect. So what we tend to do is not want to do that kind of information because we get too much ground before the pulse, overlooks the horizon. So instead what we're going to do is we're going to take this and we're going to lift it up. The lowest one we have is usually half a degree, which means the bottom of the beam is parallel to the ground. The top of the beam's up. So this half degree angle is what we call the base reflectivity at 0.5 degrees. So that's the lowest we look down. And then when we do a volume scan, we lift it up and create bigger and bigger. Now, if you look at your VCPs, you will see that we deal with different elevation sizes. Now, before I show you that, let me just go to the resolution. So here's pixels. Here is 10 pixels per inch, or 2. This is, you can tell this is European because it's 2.54, but in Europe they use a comma when we use a period and vice versa. So when we double the resolution, we're getting 4 times more pixels, and This circle looks more like a real circle. If we did it again, it would look better and better. So that if you think about your phones, I think the first phones came out, like the iPhones, with like 1 megapixel. And now I don't even know what we're at, 12 megapixels, something like that. Just great images, which means if you wanted to zoom in, it would be great resolution. You could see the details all the way up. Okay, now our radars are 0.5 or 0.95. If we go to these terminal Doppler radars, they have a narrower beam. Do you see that the resolution on the left looks a lot better? We're able to resolve details better. That's where the term resolution comes from. And so we want a narrower beam, and the 0.95 degree doesn't show it as well. Now, just so you know, we've actually developed some technologies where the beam is still 0.95 degrees, but we call it half-degree beam. And the computers are able to pretend that because it's sweeping out, it basically says, I can make the beam smaller. I get better resolution with radar. It's a high resolution response. So we are actually getting better images than we did, let's say, 15 years ago. Anybody who knows anything about the camera, sometimes you can zoom and do an optical zoom with the lens, and sometimes you do a digital zoom. It's basically the computer filling in the gaps, so to speak. Okay, so what happens to the resolution the further an object is from the radar? I want you to go ahead and put this in there, but you should know, or in your notes, you should know that it's going to be worse. The further you are away from something, the worse the resolution, because the beams are 2 miles across at 100 nautical miles. So if there's details, I'm not going to see that. It all fits within one beam. So what's better for resolution? The answer is a narrower beam. The 1 degree is better than 2 because the resolution is based upon a narrower beam. Now, here's the question, though, that I have to ask you. I want you to write this down. So hit pause right after I ask you the question and go write it down. Think about an answer. Obviously, I like narrower beams because it's better resolution. Do you also agree that it makes the power more focused? But what about pulse length? If I have more pulse length, what does that do to resolution? So I hope you thought about that. The longer the pulse length, the poorer the resolution. But if I have a longer pulse length, I'm sending out more power, I'm screaming louder, and therefore I have better sensitivity. So the one thing we can control is whether or not we have long pulses or short pulses. So if nothing is going on, do I care that much about resolution? Probably not. I want sensitivity so I can pick up dust in the air or insects that get carried along a gust front. So I'll probably use a long pulse. But when I get rain, I'm probably going to want to use short pulse because I don't need to worry about resolution. I need to worry about resolution. Let me rephrase that. I do not need to worry about sensitivity if there's rain because rain reflects a lot in the first place. So if I kind of look down at the radar and I'm looking at maybe rotation, which is inbound, outbound, I think we've talked about this before. If the tornado is here within 2 beams, I get strong inbound and outbound. But notice if there was a tornado out here, something like this, and I'm looking at raindrops that are flying in and raindrops that are flying out. Do you notice that in this region here, I don't see raindrops? In this here, I may not see raindrops. So I don't get as good detail. It's weaker inbound or weaker outbound because over there it's not spinning around. Now, what if I had a tornado out here? Notice that the rotation is all within a single beam, which means I cannot resolve that there's stuff going toward me and going away from me. So I can't resolve the tornado because it's too small at a greater distance. And that tells us why we want radar not super close to the populated areas, but relatively far. And we'll talk about that. We want to be able to resolve tornadoes being close enough. If it's too far, we're not going to see a tornado. So we don't want a big city with a radar that's 120 miles away. That's a bad idea. And there's a few places northern Missouri, for instance, that actually doesn't have a very good radar collection. Okay, so before I go to this, I want to go back to one of the notes from the radar notes. So I'm going to my academics. I'm just grabbing this, an easier way, something that I can do faster. And what I want to do is I want to go to this sixth thing. So notice in clear air mode, the most common one is going to be a longer pulse, which has high sensitivity. But remember, long pulses have poorer resolution. So I suppose there's times where, a lot of dust in the air, I don't care about it. I'll get better resolution, lower sensitivity. So it's sort of a trade-off. When I go to precip mode, notice that most of the time it's going to be shorter pulse, lower sensitivity. And why do I want shorter pulse? Primarily because I want better resolution. But on this diagram, I'm going to show you something else. Here's the radar, there's the beam. Notice what it says over here, 0.5. Ooh. It says 0.5. And that 0.5 says that's the elevation angle. So if I look at all of these beams, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And if you look a little bit above it, it says 14 elevation angles. So that's what we're looking at. That's what this chart is saying. Okay, notice too that this gets further apart, so I can actually use this to say, well, how far is that? Well, that's around 10,000 feet. That's the distance between that. And so as a result, what that tells me is that that's the beam width at that distance. So they spread out. The curve is because their beams are refracting. Remember, we talked about normal refraction. Okay, lots of cool little things about this. But now let's imagine that I got a big thunderstorm, and I'll use gray to make it a big, scary thunderstorm. If I have a thunderstorm with a base of 5,000 feet to, let's say, 50,000 feet, how well do these beams interrogate the storm? At 100 nautical miles, the beams are around 10,000 feet across. And how many beams are interrogating the storm? 1, 2, 3, 4, and maybe part of 5. I've only got 5 different ways to look at it, 10,000 feet apart. Also, keep a note that down here, I'm not even seeing the lowest 5,000 feet. The stuff of interest, maybe the tornado or something major going on, is below the radar, flying below the radar. The radar can't see it because it's over the radar horizon. Now, where's a better place to see the storm? Well, let's put it here around 30 nautical miles. Notice here I have a beam going right at the lowest level, where if there might be a tornado, there's maybe no rain, or I mean raining, but I'm not seeing the clouds. So there's a beam here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different beams are looking at it. Much better resolution. I'm able to get more details. I have different levels. I can see what's going on throughout the whole storm. So the way I look at it is I want storms to be between around 20 to 40 nautical miles from a radar. That's why Chicago and DuPage County and these really high dense metropolitan areas are somewhat situated away from Lockport, because Lockport is 20 to 30 miles away from downtown Chicago. So we're covering the populated areas really well. We also don't get as much ground clutter from buildings when there's super refraction. Now, where would the worst place to look at a storm? Well, over here. How many beams are going into a storm if it's right above the radar? And the answer is none. Okay, so imagine, look at this beam. The highest it goes up is 19.5 degrees. So watch here, 19.5 degrees. That's as high as it goes. And it makes a circle, and it doesn't see anything inside of what shape? Inside a cone. That area where we don't see it is called the cone of silence. I know we talked about it, that's on your worksheet. So the cone of silence is here, and that's the worst place for it. So if you're in Romeoville, you're not using Chicago radar to see a storm over Joliet. It's too close. So you'd have to use Lincoln, which is about 120 miles away. So it's not perfect. The best thing about it is that the Weather Service is usually co-located with the radar. So there's people who could actually go, hey, what's going on? And now we use our eyes as remote sensors. So that's what this is all about, looking at these beams. And that's what this page shows you. So we didn't really talk about that during class, but now you will be held responsible for that. So I'm going to keep this up because we're going to come back to it in a little bit. Now, where is my PowerPoint? Did I shut my PowerPoint? Maybe I shut my PowerPoint. I don't know where it is. Well, whatever, we're back. Just a moment's hesitation. Okay, now, we've talked about reflectivity. I am not going to go through this other than to say the following statements as a conclusion. Number one, DBM says that the reference power is a milliwatt. DBZ is just like this, but the reference power is that one sphere, that one spherical raindrop in a box at a certain distance. But the decibel idea is we're taking something exponential and making it linear. So the key thing is, if we double the power coming back, the return power, we add 3 dB. If we cut it in half, we lose 3 dB. Okay? And then the reflectivity is to the 6th power. So to the 6th power says we double it 6 times. Doubling results in an increase of 3 times 6 is 18. So if on the ones I did, I went from 40 dBz goes to 44 dBz if I double the raindrops. 41 dBz goes to 59 dBz if I double the raindrop size. So that's what I have to say about that. Okay, now we've talked about some of the VCPs, and these are all the numbers, and I've given you some in that handout with 11 and 12. Basically what you're looking at is clear air mode and precip mode. That's what you need to focus on. That's what you need to know. And it tells you when I would maybe use this. But there is this thing, range folding mitigation. So what it does, and we'll explain this when we get to the Doppler effect, is it changes. It switches the PRF automatically in between like pulses. Not in between pulses, but it does at one pulse for a while and then it does it again at a different pulse. So you get some weird information. If those of you who have followed radar sometimes get a lot of purple haze, the purple stuff in it, and that's because it's acting in a way that's a lot of range folding. We'll talk about that later, but if anybody's seen that, that's the reason. Now this other cool thing, this thing called SAILS, and really I'm not gonna test you on that acronym because I'm not even, if you ask me, I wouldn't even know what it stood for. I know what it is. Okay, so where's the important stuff? The important stuff to really know is down low. You know, we want to know what's happening down here. So what the radar does is this, it scans down low, it elevates for a while, and then about halfway up, it goes, wait a second, I'm gonna go back down to the ground, that surface, that lowest 0.5 degree angle. And I'm gonna look over there again. Then I'm gonna go back up higher and do that top half. So basically I do the bottom half of the storm which starts bottom up, then I go back to just the lowest elevation, and then I jump back to the middle and go to the top, and then go back to the lowest. So it takes 5 minutes to scan. The volume coverage is 5 minutes, but how often does the lowest elevation angle update? And the answer is every 2.5 minutes. So I get better, and if I want to be really cool, I will use this word. I get better temporal resolution, right? We've talked about spatial resolution. Now we're talking about temporal resolution with respect to time. And that helps a lot. So why is this good? Weak, short-lived tornadoes might actually be able to be detected. If not, sometimes you just don't do it. So this is just a scanning strategy, sales. And we have some cool technologies. We're just smart humans and make good solutions to problems. Now, the radar operates in the two modes, the VCPs, the precip mode and the clear air mode. Now, I want to show you something here. I'm going to go back to this. We have what's known as NIDS. And NIDS is the NEXRAD Information Dissemination Service. So you should be knowing this. And it basically says this: there are radars that are available for people to look. If you use your phone, you are using a NIDS product. It's what we call level 3 data, if anybody uses GR Level X. Excuse me. So NIDS data is the stuff that we go, okay, you know what? I'm not going to give you all the data. I'm just going to process an image and give you the image, your phone, the National Weather Service. We have our site, so watch this. Oh, let's try not to put dots on there. Let me just do here. Here's our site. This is an image of radar, and it is a NIDS image. This is level 3 data. I can't interrogate it. I can't do anything with it. It's just information, okay? For those of you using GR Level 3, you can zoom in on it, but it's still a NIDS data. And NIDS data is going to do something kind of weird. When it's operating in precipitation mode, the only range that it's going to give you is this range here. There's 16 colors, 16 levels. And these are what we call the VIPs, the VIP levels. Remember, video, integrator, and processor. So there's 16 VIP levels. If it starts the lowest at 5. If it's 5 to 10 dBZs, 5 dBZ increments, it's going to be light blue. If it's less than 5, what color does it get? Black. The VIP is assigning black to anything showing up less than 5. 5 to 10 is the lightest blue. 20 to 25, we go to green. 35 to 40, we go to yellow. If we had 65 to 70, we go to pinkish. If we go to a purple, 70, 75, and then anything over 75 is white. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 levels. And we range from 5 to 75 dBZs. So could there be something light over here at 2 dBZs or negative 5 dBZs? Yes. But a NIDS product, level 3 data, NIDS won't see it. Okay? And that's because it's operating in the mode is precip. Now, if I wanted to get that stuff, I have to operate in clear air mode. But look at the difference. Same 16 color levels, but this time there's 4 dBZ increments, and they go from negative 28 to 28. So if there's a big thunderstorm over here someplace, and it's showing up at 60 dBZs, it'll only show up white if they're not operating in precip mode. So depending on the VCP. and you don't want that. You want, if there's a thunderstorm, you want to go to precip mode, but the meteorologist really needs to look at it. The point is, if you look here, and I think this is kind of a cool picture. This is, if you look at the date, this is September 2nd, 2006. Not that the year matters, but it's September. So what is the radar seeing in the middle of the afternoon in September? These are actually all bugs. Bugs. Because there's a lot of bugs in the air. Late summer, they fly around and the radar picks it up. And if there's a boundary here, which there's not, but if there was a boundary, a lot of times the bugs will get caught up in a boundary and go higher in the atmosphere. And you'll see these lines showing up on radar. These are called fine lines. And it might be bugs. It could be dust. So biological or dust. And I want the low, they're showing up below 5 dBz. So I want to use clear mode to see that. Okay. So that's why we would use this. Again, I told you that snow doesn't show up well. So sometimes snow, if it's not ridiculously heavy, they'll go to clear mode to show snow. Here's an example of that. Here's a snow event. So what I did here is I took the snow and I'm like, oh, there's a big band of snow. That's the heaviest. And then there's this little north-south band and then more down here. Now, what if you were standing here? Well, use northern Cook County, you'd be like, well, it's snowing there. See, I can see it. It's coming down between -4 and 0 dBz. But if I were using the wrong mode, I would still see this band and this band, but over here, I would show nothing. So if I'm using it, I could still see some of the main features there, and there, but I don't see the details because I'm in precip mode. So that's why you typically want to use clearer mode. And when it's snowing, even pretty heavy snow tends not to get more than 24 dBz. Now you could get graupel or hail or raindrops melting, bright banding, and then you start, and if you had rain, then you probably need to go to precipitation mode. Anyway, that's what that's about. So NIDS gives you a lot of products, and I'm going to ask you a test, and these products here go along with, where's that? That's not it. Did I maybe put it here? Here, the radar notes. So here's the list of them. So it's all here. You don't need to write it down unless you want to just kind of look at this while I'm showing you these pictures. So the first one is just base reflectivity. And we get 4 different elevation angles. You always have the lowest one, the lowest 4 really. Now remember, when it's operating in precip mode, it goes up 14 levels. You won't see them if you're using a NIDS. So if you're using a radar site on your phone, by the way, if anyone's interested, the radar site that I recommend for your Galaxy phone or your iPhone is something called RadarScope. So really good professional, where am I? How can I do that? Professional grade. This is what I use. This is the best out there. If you're using the Weather Service, even the COD website, that's not as good as RadarScope. It's like one-time fee of $10 and then you get it forever. Great stuff. And if you're interested in this kind of thing, get RadarScope. Anyway, so that's base reflectivity. Then I've got base velocity. And so when I say base velocity, what I'm really saying is ground relative. That's a NIDS product. But I also get storm relative velocity. So that's a second NIDS product. We'll eventually explain that, hopefully a little bit better. So that's telling you how fast the winds are moving. We also have 1-hour precipitation totals. There's also 3-hour precipitation totals, and then storm total. So when you're watching these things, they're kind of fun to watch. Let me go to something live. I don't know if I can do this. I don't even know what's going on across the United. Oh, there's some stuff. Okay, so beautiful. I'm going to go see what's going on out east, and I can look at this and I can do a loop. And what's nice about COD website is that we by far have the greatest amount of images that are available. We can go back 200 frames to watch this. By the way, did you see how it seemed to slow down? That was going on a 10-minute update to a 5-minute. And then it went back to 10 minutes. And now when it comes by, it slows down, goes to 10. So that's kind of cool. And we're getting some good reflectivities in there. So it's probably rain. But here's your 1 hour precip total. So if you want to see how much rain you're getting, you can watch the rain and evolves. It's also great for using thunderstorm tracking. So you know, excuse me, which way that thunderstorm is moving and which, well, you can see it here. Now watch when it gets a little bit closer. You're going to see the precipitation shield starting to add up. And now we're getting totals that are up over, half an inch. What I like about storm total is that it sums this up. So if I really want to investigate whether there's going to be a flood, I can see some details here. Now I'm looking over here about 1.2 inches of precipitation that's come down. It's really cool as you can actually see where there's like banding of the precipitation in the mountainous areas here. So that's cool. That's a NIDS product. We also have something called VIL. I'm going to say it fast. VIL stands for vertically integrated liquid. It is an easy way, it's a coarse resolution to see the most intense storms. And we'll talk about this in terms of the VIL of the day coming up. But VIL stands for this. So this storm's intense, that one's intense. I've actually got some gray in there. It's pretty intense storms. I've got echo tops. How high up are the clouds? Echo tops comes in really helpful when you're looking at how a thunderstorm's going. Remember, stronger the updraft, the higher it goes. So I start looking at echo tops. When I'm out storm chasing, I put my radar into 4 panels: base reflectivity, storm relative velocity, VIL, because I want to know if there's hail, and echo tops. Those are the 4 things that I use most often. Now here's an acronym within an acronym, and it gives me the wind profile, which we'll be revealing lately, and that's called the VAD wind profile. VWP is the VAD wind profile, but VAD stands for velocity azimuth display. So this VWP is the product, is actually something we'd say that's the velocity azimuth display wind profile. That's what that would mean. So don't worry about this, just throw that under your acronym list, make sure you have it. Now, the great thing about NIDS is we can also composite the reflectivity, meaning if I'm going through a storm at different elevation angles, maybe there's big hail here for this storm, and maybe the hail's higher up for another storm. What I can do is I can add wherever I am in the storm, what's the most? I'm going to composite, I'm going to put together the highest information. So when I use composite reflectivity, it's just a fast, quick way to say, oh, big storm here, big storm there, big storm there. Right? That's what we're doing. If I go back to our sheet over, where was it? Over yonder, you will see that. Now, when I go back to our page, you will see some other things that are kind of cool here. You've got differential reflectivity, correlation coefficients, specific differential phase, or what we call KDP. Here's hydrometeorological classification. So if I want to look at that, I think this is cool. So I'm going to finish with this. We're going to talk about this. This is all from dual pole radar. But I want to show you, this is kind of cool. So over here on this side, and I'm going to let you take like a screenshot and put this in your notes because I do want you to know this and I want you to have this. ND means no data. It's dark, right? There's nothing returning signal. If I look at BI, BI stands for biological. So right now I'm looking, I'm like, oh, it's not really biological. There's precipitation. So biological would be birds or insects. And the radar can tell that. GC, take a guess what that is. GC is ground clutter. I'm going to go over here to the top for a second. HA, red, which you don't see any of that red here, that's hail. So the radar is trying to figure out what exactly it is. GR, and we have A little bit maybe of GR here. GR stands for graupel, Graupel. And those are like little snow pellets. You maybe see them bouncing around, and you'll see them probably this spring. RA, what do you think RA is? And the answer is yes, rain. So what do you think HR is? Heavy rain. But here's a cool one, and there's stuff showing up kind of around the area. BD. And we talked about this with reflectivity. What do you think BD stands for? And the answer is big drops, which I think is really amazing, right? Big drops. We will talk about why that is. WS, right before it rains, what does it become? It becomes wet snow. So the closer I am to the radar, the wetter the snow, and then it melts, and then I get this is probably where the freezing level is. Somewhere around there is let's use yellow. Somewhere around there is your freezing level. Well, let's try that again. Somewhere there, right? Then, if it's not melting as much up here in the white, that would be dry snow. And then icy would be ice crystals, maybe different types of snowflakes, maybe higher up. So very dry snow starts falling, and then as it falls, it starts to get wet, covered in water, and then as it gets down here, it starts to come a little bit more in terms of rain, maybe some big drops. No heavy rain. There you go. Two other things. UK is unknown. So if you see this color, it means the radar is trying to figure out what it is, and we'll tell you how it does that later, but I don't know. And then RF, this purple, if you heard me mention it earlier, purple haze, this is called range folding. So RF is range folding. And we're going to talk about these other products when we get into dual pol, but not yet. Okay, and if we go back to here, that takes us through the part of the Doppler that I wanted to, and the rest of this will come in a different day and a different lecture, but for now, that's what we got. So I hope that worked out well for you. I hope you take good notes, but I didn't want to use class time to do this because you should be able to understand this just by listening and taking good notes. At least that's my hope. If you've got questions, talk to me during class. Okay, everybody have a great, whenever you're watching this, have a great day.